G'day again. Welcome back to Mathematics 302. Hope everything's going well for you. Hope you're having a good morning or a good evening or a good breakfast. Uh, this is lecture 7. I'll just shrink my image as usual and we'll get into it. Down in that bottom corner is quite good. Okay, so we're going to do the Hine-Borel theorem, spaces, metric spaces, non-linear spaces, and then balls and spheres. I've just got a link down there for LibreText if you want to have a look at that. That's got some more information if you want to read that at any time. Okay, so the Hine-Borel theorem states that if S is some element in Rn, so S is a subset of the Euclidean space with n dimensions, then S is compact if and only if it's closed and bounded. So what does all that mean? So compact, a set is compact if and only if it's sequentially compact, i.e. every sequence within the set has a subsequence that converges to a point within the set. And I've listed example 2 there because it's a question and answer so that you understand what this means, and when you get a question or a problem, you'll be able to solve it, we hope. And it's closed and bounded. Okay, so closed, a set is closed if it contains all of its limit points. And you should remember that from a previous lecture. Bounded, a set is bounded if it can be contained within a finite region. So they're all pretty self-evident type of things, except for compact. Closed and bounded, sort of pretty obvious. Example 1. Very simple, very straightforward. 2 examples. Show that the set S01 is closed and bounded. I mean, you can't just say, because it's got square brackets, it's closed and bounded. You can't say that. Although it's true, you can't actually say that. You have to say it with some other argument. It's like if you're doing a proof, you can't actually use the proof to prove the proof. So if I said to you, prove that Pythagoras' theorem is true, you can't use Pythagoras' theorem. Or if you say this to a student in school, they're not allowed to use Pythagoras' theorem to prove that Pythagoras' theorem is true. They can't say, that's not allowed. So you can't say because there's square brackets, it's closed and bounded. I mean, that is the definition of saying it, but you can't use that. You've got to use something else. So same here. So let's do it. A set is closed if its complement is open. Yeah, it's pretty obvious here. So all you're going to do is the complement is minus infinity to 0, and you've got the round brackets here rather than the closed brackets, and 0 to infinity, which is the other side, which is open and unbounded. Okay, so there it's not including the endpoints, and here it is including the endpoints. Hence, 0, 1 with the square brackets is closed and bounded. So it's pretty self-evident, but just remember you can't use the actual statement as the proof. Example 2, explain how the following set is not closed. So we've got square bracket, -1, 0, round bracket, union, round bracket, 0, 1, square bracket. So explain how the following set is not closed. Again, we can't use the terminology from the question. So let's use something else. And we're using one of the 3 things we went through a few slides ago. A set X is closed if any convergent sequence in X converges to a value in X. Okay, so we're going to say it's not closed by showing that this isn't true. So -1 union, now here we're doing the union of -1, 0 and 0, 1 equals -1, 1. So we'll go with square brackets. So this is bounded. All right, so we've effectively, in doing this, we've ignored the round brackets. However, both sections of the union dictate that not including 0. Hence, 0 is not in X. Hence, the sequence cannot converge to 0, even though it approaches it from both sides. Therefore, the set is not closed. So while you're saying this, you're looking at this knowing that there's no 0 in that range, in that bounded range. So we've used this to prove it's not closed. More examples. So these are just really boom, 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 boom. Let's go. So 0 to infinity, so we're including 0, not including infinity, has in complement minus infinity 0, so it's closed but unbounded. Minus infinity to infinity has a complement empty set, so it's closed. The empty set is always open and closed, but it's unbounded. 0, 1, where you 0 is included, 1's not included, has the complement minus infinity to 0, union with including 1 up to infinity. So it's not closed and it's not open either, but it's bounded. So that's a problem. If you're trying to say it's one type or the other, well, it's not. It's not. It's not. There shouldn't be two commas there. My apologies. So 0 to infinity, not including the 0, has a complement minus infinity to 0, so it's not closed or bounded. And 0, 1, 2, 3, all the way up to forever is closed, but it's unbounded. And again, there shouldn't be an extra dot there. A few extra dots sneaking into this screen. Okay, topological spaces. So we're going through a few different things in this lecture, and hopefully they'll all join together in the next lecture. We'll see how we go, but there's a few different concepts coming through here. So a topological space is a set of points together with a topology which must satisfy three rules. The empty set and the entire set are open. The union of any number of open sets is open, and the intersection of a finite number of open sets is open. So this is just explaining a topological space, just so we can move forward. So you've got those three rules. So this structure defines concepts like closeness, continuity, and connectedness without needing a numerical distance. So we're now going to look at these three things. So closeness, continuity, and connectedness. Closeness occurs within neighborhoods. So we've got a dot and a bunch of dots around it in terms of points, where a neighborhood of a point is a set containing an open set that includes the point. Continuity is defined by a function that maps open sets to open sets, ensuring that nearby points are mapped to nearby points. And connectedness describes a set that cannot be split into two or more disjoint non-empty open subsets. Okay, so connected means it's all one. Keep those in mind. And you can read Juju's on connectedness if you want. There's some more high-level stuff for you. Connectedness question. Here we go. Suppose A union B and A intersection B are connected. So let's suppose they're connected. Show that if A and B are closed, that A and B are connected. So we're basing it on this, and we're trying to show that if A and B are closed, that A and B are connected. You could go about it a few different ways, but the main way is by disproving one of it. So we're going to assume A and B are closed and A is disconnected. That's what we're going to assume. So therefore, since A and B are closed, there must exist an open interval of a positive length where the length AB is part of A, such that the endpoints A and B are contained in A, that is A comma B, are elements of A. Right, so you've got the length is in A and the endpoints are in A. If A union B is connected, right, if A union B is connected, so we're going back to here, then the elements, so the length AB is also an element of B. Since B is closed, then the endpoints A and B must be in B as well. Okay, because we've assumed A and B are closed. But, problem, A intersection B would be disconnected since A, B are elements of A and B. Let me make an image up here so they're out of the way of the thinking space. A intersection B would be disconnected since the points, the endpoints A, B, are elements of A intersection B. But A intersection B intersected with the line AB is the empty set. There's nothing there. So therefore, A union B and A intersection B cannot be connected at the same time. So this is not true. And if we're showing that this is true, well, then one of those isn't true, and hence A and B are connected. So a lot of this discussion, a lot of your reasoning for questions will be just logic. If A is true, B is not true. Then if B is true, A is true, that sort of thing. it's really a lot of this whole subject is to do with logic. Metric spaces. So a metric space is defined as an element, a set of elements or points where a distance is defined between any two points by a function called a metric or distant function. This metric must satisfy three properties. Non-negativity, the distance is always 0 or positive and only 0 for the same point. Symmetry, the distance from A to B is the same as from B to A. And the triangle inequality. The direct distance from A to C is less than or equal to the sum of the distance from A, B, and B to C. So if you're going via a different path. So it's less than or equal, which is the same for any triangle. So here's an example. Consider x is alpha, beta, gamma, and we define the distance function with the metric space as the distance between x and y is 0 if x equals y, and the distance between x and y is 1 if x doesn't equal 0. If x doesn't equal y. Okay, we're going to define that. So if we draw that up with alpha, beta, gamma across and down, it will end up looking like that. We'll go alpha to alpha, alpha to beta, alpha to gamma, etc., etc., etc. And here you'll notice down the diagonal, you've got alpha going to alpha, beta going to beta, and gamma going to gamma. And if we applied this principle to this set of data, so you've got 0 if x equals y, 1 if x doesn't equal y, you'll end up with this. So 0's down the center and 1's everywhere else. And so if we look at that, and that obviously can lead to matrices and a whole lot of work on matrices, which we'll look at some of that next lecture in lecture 8. Okay, so if we look at this transformation by saying if it's the same, it's a 0. If it's different, it's 1. So there's a length of 1 there. There's a length to itself. Going from itself to itself is obviously 0. The question you could be asked, does this satisfy the three properties of a metric space? So the distance x to y is 1 for alpha, beta, beta, gamma, etc., etc. And dx to x is 0 for alpha to alpha, etc., etc. So yes, distance is always 0 or positive and only 0 for the same point. So yeah, we've got the first one. Second point, distance xy is 1 for alpha, beta, and distance xy is 1 for beta, alpha. So this is where it applies one way and the other way, the second point. So yes, distance AB is the same as distance B to A. And the third property is a lot of writing that I wrote. I'm having out this. The third property, which is the triangle. So distance x to y is less than or equal distance x to gamma plus distance gamma to y. So some any lambda, gamma, alpha, anything else, D, A, B, C, whatever. Oh, not D, because we're already using a D for distance. So distance x to y is less than or equal the distance from x to delta. Oh, it should be delta, isn't it? Yeah. Losing my Greek, forgetting my Greek terms. So distance from x to delta plus the distance from delta to y, right? It must be less than or equal to that. So here we go. If x equals y, then distance of xy is 0. So the other side will be 0 or 1. And if x is not equal to y, that will equal 1. So either delta equals x or delta equals y. So the addition will be 0 plus 1 or 1 plus 0, which both total 1. So that's true. We've got that one. Now, if delta doesn't equal x or delta doesn't equal y, then the addition will be 1 plus 1 equals 2. So let's suppose delta equals x, y, z. So let's suppose delta equals z. And you had to go from x to z and then from z to y. So delta is somewhere else in the field. Then the addition will be 1 plus 1 is 2, which is greater than 1. So yes, the triangle inequality is true. So they're the sort of the two different choices you can have in proving the triangle inequality. And they would be the three properties you would show, very straightforward logic, that it does satisfy metric space. Okay. Next one is normed linear spaces. Okay, so this one I didn't do an example. I think I just did the definition here. A normed linear space is a vector space with a norm, which is a function that assigns a length or a size to each vector. This norm must satisfy four properties. It's always non-negative. It's zero only if the vector itself is the zero vector. The norm of a scalar multiplied by a vector is the absolute value of the scalar multiplied by the vector's norm. And the norm of the sum of two vectors must be less than or equal to the sum of their individual norms, which is a triangle inequality. So you're effectively proving the same three things in 4 steps. I've got an example of this in lecture 8, and it goes into a lot more, we'll go into a lot more detail of examples, which you should have seen those before with vectors and matrices. Balls in open and closed sets. Just recall from lecture 3, this is just a quick review of a point in lecture 3. A ball is a set of points at a fixed radius around a point. It's a specific type of neighborhood. So we drew these images where you've got a closed set, there's a point, and there's a neighborhood. There's a point, but the neighborhood's only staying inside the closed set. In an open set, you've got a point same inside the open set, but the open set's got no edges, keeps on going. So you can have a boundary point which is outside the limit because it's an open set. So a set is closed if and only if it contains its boundary points. A set is open if and only if it does not contain its boundary points. And an example there would be 1, 3. An example here would be 1, 3 with obviously with rounded brackets to say the 1 and 3 are actually included. So that was from lecture 3, just as a reminder that you have seen balls in terms of a set of points with fixed radiuses, so included and excluded from the boundary. Okay. Next one. So we look at balls in metric spaces. So we'll go through this in 2 different ways here. So the first way, since the open interval A minus, we'll go delta, A plus delta can be described as a set of X values such that f xa, that should be a D, sorry, dx, the distance xa is less than delta. This can be extended to any open interval of any metric space. However, the term interval will not be appropriate, so we're going to replace the concept of an interval with that of an open ball. So if x, fx, and again I should have used dx there, not f, is a metric space and A is an element of X, for delta greater than 0, the open ball B, so we'll call them the open ball B, from A to delta of radius delta around A is the set B A delta equals X to X, and that should be a D there, XA less than delta. Okay, that'll make more sense in a second when we go through this. Okay, so this is hopefully making it a bit more concrete. Let's declare X, a set X, which contains X and Y. So this green bit is X, which contains X and Y. There's X, there's Y. And any 2 points that are some distance D apart. So we have X and D. So we've got this distance here from this function in this set X. So this means if we consider any 2 points and we apply this, then we have 2 points which are some non-negative distance apart. So we're going to apply D. So if we apply D, the distance xy, it's going to be something from 0 to infinity, some length. So what we have to have, what we have to have is an open ball centered around some point x. Oh, sorry. So what we have is an open ball centered around some point x. Reading too fast there. At a distance r, which is the same as having a point y in x, such that the distance between x and y is less than r. So that is this. So we've got a ball centered around some point x, distance r, so that's giving you the length of the radius of the ball. And that means y is an element of x, such that the distance xy is less than the radius. So that's really an open ball. That's really a definition there in terms of an open ball. And here you've got an image that I've drawn. There's X, there's an open ball with dot, dot, dot. So if we're considering this here in the real space, in R3, you would have seen there's something like this before. If you want to find the distance, you certainly have seen it with Pythagoras. Hopefully you've done some 3D space and you want to find the distance between 2 points. You're going to go y1 minus x1 squared plus y2 minus x2 squared plus y3 minus x3 squared. And that'll be the distance formula in 3D space. And we can consider this as a ball Bx, which is y is an element of R3. Same here, I've got y as an element of x, where the distance xy is less than some radius. And I've got a note there for you to have a look at for a YouTube clip. If we consider the points which include R, then we have a closed ball. So here I've just made this, I've colored in the circle, so it's a closed ball. So a closed ball, B tilde, XR, so X with the radius, is Y is an element of X with the distance XY less than or equal to R. So that's a closed ball. A sphere, so very similar to a ball. A sphere in a normal linear space is defined as the set of all points that are a fixed distance from a central point, which is the same as every other definition of a sphere. If we consider the points which only include the boundary points, then we have a sphere S, XR is Y is an element of X, distance XY equals R, so exactly equals R. So just two properties here. If we union an open ball and a sphere, we get a closed ball. So ball X with a radius, union with a sphere X with a radius, we get a closed ball, ball tilde X with a radius. Okay, we union an open ball and a sphere, we get a closed ball. The second property, there's always at least one point in an open ball since X is an element of that set, which is intuitively true. So X is an element of the ball XR. There's always going to be one element in a ball. That's it for this moment. I'm in the middle of writing week 8 at the moment because I was writing both of week 7 and week 8 at the same time. So I'll shortly have that up. Anyway, God bless you. Stay safe. I'll see you next time.